Alright, so to start out today, we're going to be finishing up our preliminary discussion of root spaces with rationality properties, properties of root spaces, which is going to kind of serve, I believe, as a summary mostly of what we've covered so far. So L is a semi-simple Lie algebra over an algebraically closed field, characteristic 0. With a maximal toral subalgebra H, a phi being a subset of H star being the set of roots of L relative to H, and we can then split L into this H and the union of all our root spaces, which is the root space decomposition. Since the restriction of the Killing form to our maximal toral subalgebra is non-degenerate, we may transfer it to H star as they don't write it with a function, it's also like the parentheses of these two being equal to the Killing form of their corresponding elements of H, T gamma, T delta. Now, as our root space spans H star, that is, we may choose a basis of alpha I from 1 to L of roots so for root beta we have beta being the sum of some Ci times our alpha I. For Ci in F in our field. We then have that these Ci are actually going to be rational. For each j equals 1 to L, we have that the root killing form of beta and alpha j is equal to the sum of Ci times the root killing form of alpha I and alpha j, so that we get 2 times this beta alpha j, multiplying both sides by 2 over the root killing of alpha j with itself equal the sum of 2 times the root killing form of AI and root aj over root of aj with aj times ci, which is a system of L equations in L unknowns with integral coefficients. Since our collection of roots is a basis of H star, and this, our new form here, we know is non-degenerate, so is the coefficient matrix of the system of equations, which means it has a solution and then it has to be in Q. Thus, the rational subspace E sub Q of H star spanned by all roots has rational dimension L, which is the same as our F dimension of H star. Since for lambda and mu in H star, the bracket of lambda and mu is equal to the Killing form of T lambda and T mu is the sum of alpha of our roots, alpha T lambda alpha T mu, which is the sum of the brackets of alpha with lambda and alpha with mu. And for beta, in beta being a root, we have that the bracket of beta with itself is the sum over alpha in our root system of the bracket of alpha and beta squared. So we can divide by beta squared. We get 1 over the Killing form of beta itself is equal to alpha over the roots of the Killing form bracket of alpha with beta over beta with itself. And both of these are squared, which is rational because we have seen that 2 of alpha with beta over beta with beta is an integer. Thus, the bracket of beta with itself is rational, and so the bracket of any two roots, I believe, is rational. So all inner products of vectors in EQ are rational. So we have a non-degenerate form on E sub Q. As above, the bracket of a lambda with itself is the sum of the parentheses of an alpha with a lambda squared over alpha in roots. I should call it parentheses, not a bracket. So that for lambda in this rational space, lambda bracket lambda parentheses lambda is a sum of squares of rational numbers, and so is going to be non-negative. So the form upon EQ is positive definite. Now, let E be the extension of E is going to be the extension of our rational EQ to the reals in the way I described way long ago as the Q, the rational tensor of EQ with R. The form extends canonically to E and is still positive definite. So E is a Euclidean space. Our root system contains a basis of E with the real dimension of E still being our L. And we have this all in a theorem. To summarize. So I'm just going to use our space L, the maximum total subalgebra H, root system phi, and the E that we have defined above, the Euclidean space. So A says that the root system phi spans E with a 0 not being an element of the root system. B, if alpha is an E, I think they are repeating this. The negative alpha is the only other scalar multiple of alpha in phi. Comment C, if we have two roots, alpha and beta in phi. Then beta minus 2, the bracket of beta with alpha, over the bracket of alpha with alpha, times alpha is a root, and d is that if alpha and beta are roots, then this 2 times beta parentheses alpha over alpha parentheses alpha is an integer. And we've seen this. So this asserts that our phi is a root system, which is, I think, a technical term that we haven't actually defined yet. We're going to get to in the real Euclidean space E. So we have a correspondence from the bracket of L and H, of L and H to our root system and its Euclidean space. We will completely classify these pairs of phi and E and see that this correspondence is 1-to-1 and phi does not depend on H, I think. The wording here is a little ambiguous, but that's what it seems. So now we have here 3 systems. First off, we're going to be looking at root systems here. We're going to be looking at the axioms, the axiomatic definition, I think. And then in that, we're going to be starting out with looking at reflections in Euclidean space. Throughout, we look at a fixed Euclidean space E, which is a finite dimensional vector space over the reals with a positive definite symmetric bilinear form, which we're going to write as alpha and beta, as we've seen. Reflection of E is an invertible linear transform which leaves pointwise fixed a hyperplane of codimension 1 and sending any vector orthogonal to that hyperplane to its negative. So such reflections are orthogonal preserving the inner product. And we see actually that any non-zero vector alpha determines a reflection, which we're going to call sigma of alpha, with reflecting hyperplane P alpha defined to be the beta in our Euclidean space such that the form of beta and alpha is 0. With scalar multiples non-zero, of course. Non-zero scalar multiples yielding the same reflection. We have an explicit formula and explicit formula in sigma alpha of beta be equal to, this may be a familiar formula, beta minus 2 of the form of beta and alpha over the form of alpha and alpha on alpha. And this just sends alpha to negative alpha and fixes everything in P alpha is all you need to do to check that this works. And we are going to abbreviate the abbreviation of the diagonal, this angle bracket of beta and alpha, referring to this 2 beta and alpha of alpha and alpha. Which as a thing itself is linear in the first variable and the first variable only. And we're going to do a bit of setup here. Let phi be a finite set spanning E. Suppose all reflections of sigma alpha for alpha in our phi, leave phi invariant as a whole. If there's a function sigma in the general linearly group of E, so this does have to be invertible, leaves a phi invariant fixes pointwise a hyperplane, which means codimension 1, as I kind of alluded to before. Hyperplane P of E, and sends some non-zero alpha in phi to negative alpha. Then our function here is just a reflection generated by the element of phi which goes to its negative. And of course everything else is going to match up too, like the hyperplane is going to be the same and all that. Alright, let's look at the proof. Let taf equal sigma alpha, which because sigma alpha is its own inverse, is equal to sigma alpha inverse. And then we have that taf is going to preserve our phi, and we know that taf of alpha is going to be alpha. So taf acts as the identity on the subspace where alpha, and on the quotient E over R alpha. So all eigenvalues of taf are 1, and the minimal polynomial of taf divides t minus 1 to the L, with L being our dimension of E. But since phi is finite, not all of beta, taf beta up through taf to the k beta can be distinct. So we can choose k such that we can choose some power of taf that fixes beta, such that, and so we can just k such that it fixes all beta in phi. Oh, so the idea is we have beta here in phi, k is greater than the cardinality of phi. So since the action of taf preserves phi as a whole, this has to double back on itself, and so that we can just find this value. Since phi is finite, we can find this value for every vector in phi, and just multiply them all together, and that ridiculously big power is going to fix every vector in phi. And because phi spans E, then t to the k has to equal 1. So the minimal polynomial of taf divides t to the k minus 1. Thus, with the previous info, taf has minimal polynomial t minus 1 being the greatest common divisor of t to the k minus 1 and t minus 1 to the l. So taf is 1. And yep, we are gonna keep going because it's hard to this book is harder to judge how long things will take, I find. So we're gonna look at root systems. No. So a subset phi of E of our Euclidean space E is a root system if it meets the axioms phi is finite, spans E, and does not contain 0. Kind of seems like they're cramming 3 things into one axiom there, but sure. 2, for alpha in phi, the only multiples of this alpha in phi are positive, negative alpha. This should all be pretty predictable. Third, if alpha is in phi, the reflection generates leaves phi as the whole invariant. And 4, if alpha and beta are roots, then the 2 times the form of beta with alpha over the form of alpha with alpha is an integer. And these correspond to the properties we saw way earlier. Note that we have redundancy. E.g. both 2 and 3 imply that phi is closed under negation. state that sometimes axiom 2 is omitted with our definition being a reduced root system. Alright, so let phi be a root system in E denote by a fancy W the subgroup of the general linear group of E. General linear Lie group, I guess, doesn't really matter in this context. Generated by our sigma alpha for alpha in phi by condition 3 our W permutes our root system which we recall as finite and spans E. So we can identify this W with a subgroup of the need a new page of the symmetric group on phi. Giving us that this W is finite. This W is called the Weil group of our root system, and this will be very important later on. So we can have a lemma detailing how automorphisms of E act on, certain automorphisms of E act on this Weil system. Lemma. Let phi be a root system in E with a Weil group W. You have a sigma in the general linear Lie group of E leaves phi invariant then sigma alpha conjugated by the sigma is equal to sigma of this sigma of alpha. Kind of confusing how they decided to write things out. For all alpha in a root system, and the bracket of beta and alpha is the bracket of sigma beta and sigma alpha for all alpha beta in phi. And there's a proof with this, of course. See that sigma alpha, and sigma inverse of sigma beta is obviously going to be sigma alpha of beta, which is going to be a root still. But this is just sigma of beta minus bracket of beta and alpha on alpha. I'm gonna just write this on a new line. This is equal to sigma alpha of beta is sigma beta minus the bracket of beta and alpha on alpha by definition of the reflection, which is then going to give us sigma beta minus the bracket of beta and alpha on sigma alpha. We can just split sigma across all this. Since beta runs across our root system, since sigma of beta runs across the root system as beta does, we see that sigma of sigma alpha of sigma inverse leaves our root system invariant, fixing pointwise the hyperplane sigma of the hyperplane of alpha, and sending sigma of alpha to sigma of negative alpha. By the previous lemma, by a previous lemma, sigma alpha, sigma inverse is equal to sigma of sigma alpha by, and so by sigma of sigma alpha of sigma beta be equal to sigma beta minus sigma beta of the bracket of sigma beta and sigma alpha multiplying by sigma alpha. We are done. All right. Now we're going to call a root system phi on E and a root system phi prime on E Euclidean space E prime isomorphic. If there exists a vector space isomorphism phi from E to E prime, sending root system to the other root system such that phi of beta and phi of alpha is equal to the bracket of beta and alpha for each pair of roots. In our root system. Thus, the reflection generated by phi of alpha on phi of beta is phi of the reflection generated by alpha on beta. Thus, this induces an isomorphism sending sigma to phi of sigma of phi inverse of vial groups. From the previous lemma, lemma doesn't need to be capitalized, but it's too late now. An automorphism of the root system is an automorphism of the Euclidean space, leaving the root system invariant. And we note that we can regard the vial group as a subgroup of the automorphism group of the root system. So we're going to let, if alpha's root, alpha caret is going to be 2 alpha over the form of alpha with itself. We're then going to call the subset of E corresponding to these things the dual or inverse of phi. This is your root system 2 of E with a vial group isomorphic to our normal vial group. We have that in the context of a Lie algebra, basically the work we did in the preceding chapters, alpha corresponds to our element of a root in the algebra, while the dual of alpha corresponds to the H alpha under the killing form identification. The killing form identification of H star with H. And we will go through one more section because this one's going to be pretty short, I'm thinking. And this one is going to be examples. So we're going to call L being the dimension of the Euclidean space. We're going to call it the rank of the root system phi. For L is less than or equal to 2, we can draw the root systems, which is where my inability to work with this is really going to shine. When L is 1, there is only one possibility called A1. And of course this is just a plane, so we just have like two vectors. This is alpha and this is negative alpha. And that's our root system. I'm thinking there's not really anywhere else to put roots, right? Because they can't be collinear. So that's everything. This is a root system with a Weyl group of order 2. Because I'm just swapping them and then just leaving them the same. As a Lie algebra, it belongs to SL2 of F. We will now show four possibilities in rank 2. I don't think they're all of them, but it's just like a good image to have. Call this one alpha, call this one beta, and you see this is just R above A1, essentially two independent copies of it. We have this sort of like hexagonal pattern. I encourage you to look these up, like actually what they look like, because my diagrams are not going to be, you know, to scale. But this one is A2, we have alpha here, and beta, and this third axis is just their sum. We then, I'll just try to cram them on one page, which is a bad idea. We have beta 2, which is like our A1, and then we just have the diagonals like this. We just need to label the 1 going forward and back, and then we have an independent one like that. That's our beta 2. And we have a G2, which I am going to really butcher. So we have these like long ones going up and down. And then we have inside of this, we have this like off. We have these short ones, which give you a kind of hexagonal pattern. And then in between here, we have some more like big ones in these two like gaps. And once again, we can just call this alpha and this beta, and you can get the rest by adding, like these four are all supposed to be in a line like they are at the bottom. I somehow wasn't paying attention to that. I somehow managed to subconsciously get them aligned at the bottom but not the top. And so that's a good image of what the root systems look like. Yeah, it's a real good image. And I think we'll call it there. There's one more section in this section. I'm always off by one, but we're already like well over time, so I think we'll call it here for now.